The heck is that? No idea. Hey, there we go. Wonder if I need to be closer. Maybe a little bit. That's not too bad. Not too bad. I wonder if anybody showed up. Let's see. No, nobody's here. We need some students. I don't see any. But it's early. It's only 9:17. Okay. All right. Well, let's see what we're going to study today. It's that buckling. We're studying buckling. And I thought I'd do F13.6. That'd be a good one to work on. I forget what I told the students to do. Let me dig around here. Maybe I can find out what I told them to do. Let's see. I think it might have been 13.3. I wish some students would log in and tell me if that's what we were doing, 13.3. Come on now, somebody. Hey, it's 9:20. I need some customers here. No, we don't have any customers. Dang. Okay, well, we'll just have to wait and see. Hello, testing 1, 2, 3. Hello, world. Hello, students. Come in, students. Testing 1, 2, 3. We're still studying buckling. Okay. Well, I could draw this F13.6 and we could talk about it, I guess. We got 10 minutes. Somebody needs to show up. Students, where are you? Where are my loyal students that show up early? They're not here. Okay. Let me put this one on the board then. Okay, this one's got it's got some smooth pins there. Smooth pin there. Smooth pin there. And this has a distributed load. So let's put that on there. This problem that I'm doing here is problem F13.6. It's on page 992. And this is a distributed load. They use a little symbol W for that for some reason. I bet you have a smooth pin over here too. Yeah, that's supposed to be straight up and down. Let me do that better. It's not quite right. Yeah, that's a little better. Okay. Let's see if we got any customers signing in here. Okay. Nope. Nobody's. I'm starting to feel unloved here. No. Oh, there we go. Gavin Jackson. Hurrah. You signed in. Good. Now we have two of us, Gavin. But what happened to my nice picture I had? Maybe I need to click on that. I don't know what I need to do. Gavin's got a nice big G there on his thing. Yeah, there we go.
That's from my Google account. I made mine through.
I like it. It's got class. But how do I get rid of it? It's kind of over here in the corner of my picture. Oh no. I can't seem to get rid of it. Wait a minute, I can minus it. That didn't help any. I don't know. But we have two of us, and I was going to do this F13.6. Gavin, do you happen to know? Yep. I told you guys to do a problem. Was it?
I have 13-3.
Yeah, that's what I need to do with you guys. Yeah. We probably should start with that. Let me erase this and we'll start with 13-3. We'll get to this. I hate to erase that though. I did such a pretty job on that.
Yeah, it looks good.
Yeah, that F13.6. Maybe I'll go ahead and do that. They said this was 6 meters. And this was 3 meters. We'll do that. And then we're going to do the one you said, which I think is 13.3, right?
Yes.
Yeah, we'll do that.
Sounds good.
Yeah, that's the big plan. Okay, now the problem is, something bad happened. How do I get back to Gee, I don't know what to do here. Okay, there we go. Hey, we got some more customers. Look, we got Dalton and Eric and Daniel and Cameron. We got a pretty good crew here. But I need to, oh, here we go. I need to do this pin thing. Yeah, now we're cooking. Yeah, there we go. I thought we'd start off by doing this F13.6. It's on page 992. Let me read it and see what they want us to do. I think they want us to find this distributed load. See their little symbol W, that's their secret symbol for a distributed load. All right, let me look this up here. Page 992. We don't have 900 pages in this book. Something screwy here. We don't have 992 pages in our book. You suppose I meant 592? Let me try.
It's on page 678.
Oh, okay.
But I think it says it's A99 or 992 steel, so that might be where you got it.
Oh, yeah. Now was that my friend Gavin just now?
No, it was Eric.
Eric, I'm gonna give you a thank you point, Eric, right over here. That's your first one for today. It's not on page 992. It's on page 678, like Eric was trying to tell me. But it is A992 steel. Now let's look that up in the back. Go to the back and look that up, and it says here, 200 gigapascals. We need this. We need that there. That's called the modulus of elasticity for that type of steel, that 992 structural steel. Yeah, good. Excellent. Now what? Let me read this. It says here, if you just tuned in, we're doing fundamental problem 13.6. It's on page 678. And they want us to find that little W thing there. Okay. And now wait a minute, they said it has a factor of safety of 2. Let me write that down. So there's all the information. Wait a minute, I didn't label that A and B and C. So we'll label these. There we go. I think we're in great shape now. But see, this is what they want. That's called a distributed load. Some people call it a line load, a line loading. You can also have surface loading and volume loading. See, right now, every one of you guys has a volume loading because every particle of your body is being attracted to the earth by gravity. And it's a volume loading because your hands have mass and they're attracted to the earth, and your elbows have mass and they're attracted to the earth. Your intestines, the whole thing is of your body. It's a volume loading. There's also surface loadings, but this is a line load. But in general, we're talking about distributed loads. There's different kinds. And their little symbol in the book is a little W for a distributed load, and they want to know what that W is. Okay, well, we're going to give it to them. Here goes. we got all our information I think we need. And you know the drill. You get out your red color and you put your force right here in red. There it is. And what that is, it's the area. So the thing to remember about distributed loads, here, I'll write it for you. If you have a distributed load, there are two things that you know. You know that the area of the distributed load is equal to the resultant, the resultant. So the area of this is the base times the height. It's a rectangle. So it's just equal to 6 times W. Ta-da! And that's what this is. That's the resultant. The two things that you know about distributed loads. One is that the area of the distributed load is equal to the resultant. The other thing, I wonder if any of you remember what the other thing is about distributed loads. I could ask somebody. That'd be fun. Let's see. I'm going to go here, and we have some wonderful students here. Eric just got a thank you point. Eric just helped me. Let me pick on Eric. Eric, there's two things we got to know about distributed load. The area is equal to the resultant. See, that's the resultant. And something else. What is, Eric, what is the other thing that we have to know about distributed loads? Go for it, Eric.
To be honest, I can't think of it right now.
That's okay. Yeah, I'll give you a hint. The other thing you need to know is that the place where it's applied, where that resultant force, see that's the resultant force right there. You could call it.
So that it goes through the center, right?
That's it. He's got it. The resultant force. Why don't we call it maybe, I don't know, R for resultant? That's a nice name. The resultant force goes through it's located at the centroid, or the center. Eric said center. I'll go for that. Those are the two things we know. And what you see, here's where the center is. It's right there. That's the center. Okay. Now let's take a moment about A. Here we go. We're going to take the sum of the moments about point A. Oh, wait a minute. I didn't put all the forces on here. There's going to be a force doing this. We could give it a name. We could call it C. That'd be a nice name for it. And there's going to be a force here. And we could call that A. That'd be another nice name for that one there. And guys, I think we're done. I think that's it. Okay. So you take your moments about A, and you'll have that R, which is 6W times 3 meters. See the distance from here to here is 3 meters. And then that's a positive because it's counterclockwise. And then you have a negative C times 6 meters equals 0. So you can solve that for C, and what you'll get is, when you're all through, you'll get C is equal to, well, I guess 3W, huh? Ta-da. We still don't know what W is, but we got what C is. It's equal to 3 times the W. Now keep in mind that W is newtons per meter. So see what this is 3 meters times something newtons per meter. You're going to get newtons. Okay. Well, what we want to do is make this the failure, the buckling. We want to make that. Oh, look at all these wonderful students. Look here. I've got Eric and Daniel, Dalton, Cameron, Allison. Let's see who else I got here. Coy, Gavin. Wonderful class here. Okay. Right now, I wanted to do this F13.6, and that's what we're doing. It's on page 678. And we made some progress. We know this value of C here, it's 3W. But see, we want this thing to be right at buckling. It's almost going to fail. So what we have to do is use that Euler equation. Need a little area here to write on. Let me erase some of this because I need the room. We're going to write the Euler equation now. Here goes. This is the Euler equation for buckling. And it goes like this. I don't know why they picked these symbols, but they said P there. What we want is the C. But it goes like this. Now this is 2 pins. We got a smooth pin at B and a smooth pin at C. So there is no, what do they call that? Effective length factor. It's just like that. Okay, well let's see what it would be. Here goes. That'd be pi squared 200 gigapascal. Oh, we haven't done the I yet. Wait a minute. I forgot to read that. These are round, aren't they? Yeah. Let me read that. We're looking. This thing right here is round. It's got a circular cross section, and it says here 50 millimeter diameter. Okay. We're talking about 50 millimeter diameter. So what we want for the moment of inertia, yeah, I got some room someplace. Yeah, we'll write over here. It's going to be pi over 4, 0.025 to the 4th. Look in the flap of your book. If you got something that's round, the moment of inertia is pi over 4, r to the 4th. Ta-da! See, the r would be 25 millimeters, which would be 0.025 meters. Okay, here we go. We're going to get our moment of inertia. See, look at here. We know what pi is, and you square it, and we know what E is. We just looked that up. And the L, we know what L is. It's 3 meters. Yeah, now we're going to get the I now. Here it goes. It's equal to pi divided by 4. 0.025 to the 4th. Well, I'm getting a number, 3.0679, blah, 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 times 10 to the minus 7 meters to the 4th. All right, so now I have that. It's in my calculator. And, oh, I didn't finish writing that. Okay, 3.06796 meters to the fourth divided by 3 meters squared. This should give us the buckling load for this BC thing here. Here, I'll put a circle around it so you can see what I'm going to do in my calculator. Here goes. I'm plugging all that in now. Here goes. Oops, wait a minute. Auga. I forgot the times 10 to the minus 7 there. Shame on me. All right, here goes. Take that times 200 e to the 9th times pi squared divided by 9. I'm coming up with a critical load, which is equal to 3 little w's, equal to 67.29 kilonewtons. Anybody getting that?
That's what I got.
Yay. Yay. Okay, so now we can solve for that little w. See that 3 is in meters. And so this W will be newtons per meter. All right, I'm going to do that now. Divide that by 3. All right, here's what I'm getting. I'm getting the little w is equal to 22.43 kilonewtons per meter. Okay, let's see how we did. We just did a problem that I thought was interesting. It involved a distributed load, which didn't do you any harm. To review that, didn't hurt you a bit. And this was problem F6, 13.6. I want to see what their answer is. Here goes. I'm looking it up now. F13.6. Okay, F13.6. I'm getting there. Okay, F13.6. They said it's 11.2. Oh. We didn't do that factor of safety thing. I think this is the right answer if you had a factor of safety of 1, which basically is that's no factor of safety at all. But remember, in this problem, they said you had a factor of safety of 2. Okay, well, let's do that. I think we did everything right. I just need some room here. Now here's how it works. The factor of safety is equal to your failure load, which we just figured that out. That's 22.43. We know, divided by your allowable. Now in this case, it's not the load, it's the distributed load. But see, the failure load was 22.43. The factor of safety, that's not right. The factor of safety is 2, and this is 22.43 kilonewtons per meter. And the allowable distributed load, well, it would divide that by 2. It would be 11.21. So the answer is W is 11.21 kilonewtons per meter. And you'd still have a factor of safety of 2. You're not anywhere near failure. And the answer book says for F13.6, they said it's 11.2 kilonewtons per meter. Ta-da! And that's what they said. The book agrees with us. Any comments or questions so far? Well, okay. Let's do that one I told you guys to do. It was problem. Oh, gee, I don't remember. I'll find it here. We're talking totally organized. Okay, totally organized. Right. 13.3. I told you guys to go work that. So let's do that together. Make sure we can do that. That's 13.3. Hey, I added up all your homework. I haven't posted it to Blackboard, but I will. I promise I'm going to post everybody's homework score to Blackboard. I've got it added up. I got to find this 13th. There it is. All right, I'm going to erase all this if you're happy. We just worked a fundamental problem, using the Euler equation for buckling. If you're okay, I'm going to erase it. Here goes. I don't hear anything. All right, goodbye. Goodbye to that one. We'll just work problems here for a while. And this is our last meeting, so if I can think of anything that would help you on your final exam, I'll mention it, okay? That'd be good. Now this is problem 13.3. It's on page 679. 13.3, okay. It's an aircraft linkage. You know, when you turn the wheel that way, it there's these linkages that operates the ailerons, and that makes the plane go, and you go into a bank, either a left bank or a right bank. It's got links there. Well, all right. Of course, now that's the old-fashioned planes. I'm sure the new ones are all fancy-wancy hydraulic, or maybe even digital. I don't know. Okay, so this is A992. I shouldn't have erased that, doggone it. Let's see if I can remember. Was that the 200 gigapascals, or is that wrong?
No, that's right.
Ah, see, I can remember stuff. Yeah, maybe.
Wait, actually, no, it's not, because
Oh, it's not.
this is in English.
Oh, it's no. It has to be in English, senor. So let's go back here and look up the English. It's 29 MSI, isn't it? You know, that's a good thing for you guys to sort out when you do your stuff. If it's in English, do it in English. If it's in metric, do it in metric. Don't do like I was starting to do and screw it up. It's an English problem. You don't put metric stuff in there. All right, well, here, let me draw the picture of this thing. It's just a rod. And we're going to have compression. See, buckling is strictly compression. You don't have buckling with tension. It's when you have compression that things buckle. Now we got 4 kips here. That's English, senor. 4 kips. And then we have 18 inches. Now, I had a student once with a problem like this, and they said, well, we have 4 kips here and 4 kips here. That must mean that we have 8 kips inside. But that's not right. You don't have 8 kips inside that. See, if you take a section anywhere in here, doesn't matter where, just take a section. Guess what you have inside? You don't have 8 kips inside. Because the sum of the forces on anything in this class has to be 0. If you got 4 kips there, I had that going the wrong way. You can't have 8 kips there. You have to have 4 kips there. The sum of the forces is 0. We know that. Why am I telling you this bonehead stuff that you guys already know? Okay, well, we have 4 kips compression forces on each end of this link. It's 18 inches long. It's A992, and we looked that up, the modulus of elasticity. What do they want us to do? Oh, they want the smallest diameter of the rod to the nearest 16th of an inch so that it won't buckle. Okay. Back to the Euler equation. This is the critical load for buckling. If it's pin connected at both ends, it's just a simple L squared. So let me put that in there. Here goes. We have pi squared, 29 MSI, 18 inches squared. But we have this I here. We got to figure out what I is. See, I is 1/4. Well, it's pi over 4. The radius to the 4th. Now, they wanted the diameter. We'll get the diameter, but we're going to get the radius. I asked you guys to do this, and I know you've done it, but it probably won't hurt us to go over stuff. Okay. Well, let's put that in here, shall we? Pi over 4 r to the 4th. All right. Now what? Well, we already know what this is. It's 4 kips, right? We want it to be 4 kips. So here we have an equation. There's only one unknown. There's only one unknown. All right. Well, I'm going to put all that in my calculator and solve for r. Here goes. 4e to the 3rd times 18 squared divided by pi squared divided by 29 e to the 6th times 4 divided by pi again equals something. And then I have to take the 4th root of it. Let me do that. And I got a radius of 0.275, bunch of 5s, inches. But that's not what they want. They want the diameter. So multiply by 2 and get the diameter, and I'm getting 0.5511 inches. But they want it to the nearest 16th. Okay. Let me make some room here. Now 5/16, no. 8/16 is 0.5. 9/16, I don't know what it is. But 9/16 is 0.5625. That's what we want. See, that's bigger than that. That'll give you a little bit of extra metal there. It won't buckle. That's the answer. 9/16. Now look in the back. 13.3. I'm convinced that's the answer. Let me go back and see here. 13.3, 9/16 inch. That's correct. That's what the book says. The book says 9/16. So we got that one. That was a good one. I'm tempted to do some of these others. There's some wonderful problems here. But I'm not going to give you a really hard one that'll take you 3 hours to work on your final. I'm not that mean a guy. I'm not very nice, but I'm not that bad. But I think that's probably enough on buckling, unless you have a comment or question. I'll leave it up to you. Does anybody have a comment or question? Well, I still think we maybe should do another buckling problem, though. You know it's going to be on the test, so let's do a nice easy one, not one of these real hard ones. Something like that one there. Okay. Let me find one that I like here. How about, yeah, let's do, I forget what I've done and what I haven't done. Did I do 13/14 for you guys last time? Does anybody take notes?
I don't think we did.
Let's do it. Let's do 13/14. Let me find it here. 13/14. Yeah, here we go. Okay. All right. If you're happy with this one, we're going to erase it and we're going to do 13/14. Here goes. We are doing problem 13/14. It's on page 681. And you have a wide flange beam that's a W8 by 67. And it's A36 steel. This one's going to be an Inglés, senor. It's 25 feet long. It's one of these kind here. Artists. Oops. Well, I tried. Artist rendition. It's 25 feet long. And they said you can assume it's pinned at the top. Go to the back in the tables and find this table of wide flange beams. It's on page Appendix B in the back. They have some channels, some L shapes, some wide. Hey, here we go. W8 times 67. I found it. W8 times 67. There it is. Now, there has two moments of inertia. You want to pick the smallest one. I am on page 807. And one of the moments of inertia is 272. The other moment of inertia is 88.6. Now you want the smallest one. Now the reason for that, see, this one here, that's if you try to bend this thing this way. See how you're trying to bend it that way? But this one here, the 88.6, it's kind of hard to explain, but that's trying to bend it towards you like that. You're bending it like that. Let's look at our Euler equation. It goes like this. The critical load is equal to you see the critical load depends on I. And you want the smallest I because that'll make the critical load the smallest critical load. And it will buckle at that smallest critical load before you ever get to a bigger critical load. It's already buckled and come crashing down. So does that make sense? You want the smallest number here you want this one. Because this smaller number will give you a smaller load that will cause the thing to collapse, to buckle. That kind of makes sense. You'll never get to the bigger number. So you put in that bigger number that makes the critical load bigger, but you'll never get there because it's already crashed. Okay, so we're going to solve for this. I think that's what they wanted. So let's see what we got here. We got pi squared. We have to look this up in English, senor, English. What is it in English? It's 29 MSI, isn't it? 29 KS. No. It's 29, yeah. 29 MSI. And we're going to go with 88.6 inches to the fourth. Yeah. Divided by, now you got to turn that into inches. So what's 25 times 12? I think it's 300. You double check me on that, and you have to square it. Okay, we're going to plug all this stuff in. And we're going to get the pounds that will cause it to buckle. And it's going to buckle this way on this one. It will buckle. How do I explain this? Well, I think I tried to explain it. Here goes. I'm plugging it in now. Pi squared times 29 e to the 6 times 88.6 divided by 300 squared. Okay, I'm getting a critical load for buckling for this wide flange beam of 200, I think I'll just round it up, 282 kips. 282 kips. And I think it's gonna buckle about this axis here. Like I was telling you. Okay, let's see what the book says here. Look up problem 1314 in the back, and we'll see what they said. Maybe then we'll do some more. Okay, 13, 14. Now for your final, if you wanted to review, I'm going to post these Sunday afternoon or evening. But you could review your, I've given you test 1 and test 2. Why don't you review those? That'd be good. Now this is 13, 14, and it says here 575 kips. That's not what I got. I did something wrong. Now let me see what I did wrong. The book says 575 kips, 13, 14, 575 kips. Okay. Oh, I didn't read that part. You know, it helps to read the problem. Hey, that's an idea on your final exam. Read the problem. This says it's fixed at the base and pinned at the top. There is a K here. Remember I was telling you about this thing here? I put in the wrong equation. And if you look that up, if it's fixed on one end and pinned at the top, that K is equal to 0.7. I didn't read that. So this is wrong here. It's not 300. It's 0.7 times 300. Let me see what that is. I got a theory that's, I think my students sometimes learn more from my mistakes than they do if I never made any mistakes. But I didn't read the problem. I didn't see that K thing there. Now, if you do that, you'll get a different answer. Let me try it. Here goes. I'm going to try my new answer now. 29 e to the 6, 88.6, 210 squared. I'm getting 500 and, you know what? I'm getting 575 kips now. And the book is usually right, I've noticed. They're not always right, but they're usually right. I'd say probably about 97% of the time. So we got that one under our belts. Read the problem. Okay. Any comments or questions on that? Well, I don't hear anything. Okay, well, let's maybe do another one. I don't know. Let's try this one. So you guys are all happy on that. Let me look at my participants here. Got these wonderful students. We got Daniel, Dalton, Caitlin, Cameron, Allison. There's some others here. Coy, Mohammed, Heath, Gavin, Eric. So you guys are all happy with that and ready to move on, I guess. Okay. All right, let's do another one. Now, you tell me if we've done this before. I forget what we've done and what we haven't done, but this is 1318. We are going to do problem 1318. We're going to do problem 1318. And then I think we'll have question and answer, or maybe a review. I could ask you some stuff from previous chapters, because the final is comprehensive. But on this one here, we have a 10-foot wooden column. Okay, let me draw that. It's a 10-foot wooden column. That's it's 2 by 4. If you look at a cross section of it, artist rendition here, it's 2 by 4. Are they inches? Yeah, they're inches. This is a 10-foot column, and the bottom is fixed and the top is pinned. That's like that last problem. So the effective length, they call this the effective length. On that last problem, it was 0.7, so it'll be 0.7 on this problem. The wooden column has the dimensions shown. Determine the critical load if the bottom is fixed and the top is pinned. They said the modulus of elasticity, they gave it to us. Wasn't that nice? They put a little W there for wood, I guess. But there's all kinds of wood. They just mean this particular kind of wood. It's 1.6 MSI. And they said the yield strength is 5 KSI. Okay. So here goes. We're going to do this one. Now, first of all, I want you to find, I'm going to shut up for 2 minutes. And I want you, there's 2 different, what do they call those, moments of inertia? There's one about the x-axis, and there's one about the y-axis. I will be quiet for, I don't know, a couple minutes while you do that. Go ahead, please, and find those, and then we'll solve for the critical load. Well, I'll let you work on it for a while. Now I'm going to tell you what I think for the moments of inertia. Now about the x-axis, what that is 1/12. The 2 got erased there. 1/12, 2 inches times 4 inches cubed. Okay. I can't do that in my head. Well, I did that and I got 10 point, a bunch of 6s. Now we're going to do it about the y-axis. Now that's 1/12, 4 times 2 cubed. 1/12 times 4 times 8 equals 2.66, a bunch of 6s, inches to the 4th. Now, which one is it going to buckle about? It's going to buckle about the y-axis. You guys can see that. This is what we want right here. We want the smallest. Okay, now let's do the equation. Here we go. The critical load is going to be how's that go? Pi squared E 1.6 MSI EI. You'd use the 2.666 all over. Now watch it. It's 0.7 times. You have to put that in inches. It'd be 120 inches. And that has to be squared. Okay, there goes. All right, pi squared times 1.6 e to the 6 times 2 point bunch of 6s divided by this stuff squared. Okay, I got an answer. I'm coming up with 596, I don't know, you could round it off, pounds. Or you could say 5.97 kips if you wanted to. Well, I want to see if that's what they said. This was 1318. We're doing that one, 1318. It says here, 1318. Let's see what they say. They said 5.97. Well, that's what they said. That's exactly what they said. 5.97 kips. And you understood that, didn't you? Any comments or questions on that? Okay, well, we've studied.
Sorry,
Yeah, go ahead.
One question.
That's Heath, isn't it?
Yes. So
Yeah.
why did you choose the 2.66 instead of the 10.66?
Oh, thank you for asking that, Heath. In this equation, P critical load equals pi squared EI all over KL squared. You know what? All of these are just constants, really. But when it comes to this I, Heath, you have a choice. It can buckle about this axis here, or it can buckle about this axis here. And you have to decide, well, I wonder which way it's going to buckle. Well, looking at that, you can see that it wants to bend. Here, I'll put my ruler there. it wants to bend like that. See how I'm bending that ruler? That's how it wants to buckle. It wants to buckle about this axis. That's the y-axis. Just remember this, Heath. Pick the smallest number, because if you pick the smallest number here, you will get the smallest number here. That makes sense.
Okay.
Now, you understand now, don't you?
Yeah.
Yeah, he got it. By Jove, he's got it. Okay, good. Anybody else? So just remember, don't screw up. Don't put the wrong moment of inertia in there, because you'll get a figure that's way too big, and the thing will have already collapsed long before you reach that, what you thought was the critical load. Okay, well, good. All right, well, let's see. We've had a load of fun, and we could do a question and answer or review thing. There's going to be stuff on this final from what we studied before. I thought we could do a problem out of the chapter on torsion. Let's do one of these problems on the chapter out of on torsion. Now here's one here, but the floor is open for your questions on anything. But I was going to look at this one here. This is 541. See, that's chapter 5. Chapter 5 is torsion. What that is it's a twist, or it's a moment about your axis. See, you've got a piece here, and what we're doing is we're twisting it. Well, like I represent this with a double arrow like this. These are what I call external torsions. See the double arrow head? I mean, those are double arrow heads. And this would twist you clockwise, and this would twist you, well, it's really clockwise also, but the whole piece will twist. Yeah. Okay, now on this problem here, this is A36, it's 2 meters long, so we're in SI, and it's A36. Go to the back and look up metric system, SI, A36, and it says there, well, I think we need the G. I believe we need the G is 75 gigapascal. I think the formula that we want, well, there's several, but one of them goes like this. You might have forgotten that formula by now. That's called the torsion formula. Sometimes I get mixed up and I write these different, but that is supposed to be for shear stress, and that's supposed to be for torque. But you can always tell what units are by their, you can tell what quantities are or what the algebraic symbols mean by their units. See, this would be in Newton meters, because it's, no, I did that wrong. This would be in pascals, because it's in stress. Well, usually it's kilo or mega, probably megapascals in this case, but that's just a metric prefix. This is going to be in Newton meters. This is going to be in meters. And this thing here is called the polar moment of inertia. You might have forgotten about that. It's in meters to the fourth. But when you get through here, you'll have newtons per square meter. Well, that's what pascals are. They're newtons per square meter. Never mind the M, that's just 10 to the 6th. So we're happy with that formula there. Now, is that what we were going to use? Let me read this problem, 541. Steel shaft, 2 meters long. Outer diameter, oh, outer diameter. Is it solid? No, it's tubular. Okay, well here, let me draw a picture of it. Yeah. Oh, this is a lovely little problem. This has got a outside diameter of 50 millimeters. The outside diameter is 0.050 meters. But it has an inside diameter. I just don't know what it is. I don't know. How about we call it D with a little I there? How's that for inside diameter? There we go. It's rotating at 40 radians per second. Let me write that down. Oh, gee, we're going to need another equation that goes like this. The power transmitted by this shaft is the torque times your angular velocity. Now they gave you your angular velocity. It's given. Let me write it down. They said it's 40 radians per second. So we know radians are really dimensionless. You could just say 40 seconds to the -1 and it would be okay with me. So there's your omega. It transmits 25 kilowatts of power. They give you that. They said the power is 25 kilowatts. So look here, guys. We know what the power is. We can solve for the, what does this stand for again? This T thing here? That's called the torque. See, this stuff on the outside is called torsion. But if you section it and you look inside, you'll have to have an internal torque. They call this torque inside. Torque is internal, torsion is external. Okay, blah, 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 meter of the, determine the smallest thickness of the tube if the allowable shear stress is 80 megapascals. Okay. What they're going to do is they're going to give you this. They're going to say the allowable shear stress is 80. Let me write that down someplace. 80, allowable shear stress is 80 megapascals. You can put a little allowable underneath there if it makes you happy, right here. And we can solve this equation now, because first of all, we're going to get the torque. This is 25 kilowatts. And the omega is 40 radians per second. So I'm going to solve that and I'm going to get my torque. Here goes. The torque is 25 e to the third divided by 40. I'm getting a torque of 625 Newton meters. Aha, looky here, we got that. So now I'm going to write my equation and solve it. I just need some room here. Lots of room up here. I'm going to write this equation right here now. we know that, I got lost there. Oh, yeah. We know what that is. It's 80 megapascals. And we just solved for the torque. It's 625. And the rho, see, the rho is the distance from the center. If you want the maximum shear stress, you want to have the outside radius. Well, we already know what that is. The outside radius is, well, no, we don't know what it is, do we? Or do we? I got lost. Let me read it just a minute here. And oh yeah. Well, the outside diameter is 50, so this is going to be 0.025 meters. Yep, and then you have to divide by your polar moment of inertia. But the thing is, that's pi over 4, 0.025 to the fourth minus, what are we going to call this? The inside radius, maybe? How's that? Minus the inside radius to the fourth. See, there's your polar moment of inertia because it's hollow. It's not just solid. You're going to have to subtract this stuff that's not there. I think that's it, guys. We just have to solve that equation and we'll have it. Okay, here goes. I'm plugging all this into my calculator now. Boy, that was kind of a tough one. Okay, here we go. We're going to plug all that in. We never did use this G thing, did we? No, we didn't need it. See, that comes in with this equation here. It relates the strain to the stress, but we didn't need it. Okay. So here goes. I'm doing all this now. 625 times 0.025 divided by 80 e to the 6. Okay, and then
Mr.
what?
Griffin,
Yeah, I'm listening.
isn't it the polar moment of it's just supposed to be pi over 2?
Yes, absolutely correct. Honkin' thank you point for my friend Coy. This is wrong. Coy, bless you. You're absolutely right. Go to the flap of your book, front flap of your book. And they don't have that. Why don't you write that in? Why don't you write in? See, what they have is they have Ix is pi over 4 r to the fourth. And they have Iy is pi over 4 r to the fourth. But what we want is j. Now, j is Ix plus Iy, and that's pi over 2 r to the fourth. Coy really is very helpful to me. Why don't you write that in the flap of your book? Get your pencil. I'm going to do it too right now. And I'm going to write in there j is equal to pi over 2 r to the fourth. You do it too. That'd be good. Get your book out and do that. Now let's solve this. Here goes. This is a little bit of nasty algebra, but we can do it. We can do it. I have faith in us. All right, here goes. Okay, 625 times 0.025 divided by 80 e to the 6 equals all of that. Then you'd have to divide by pi multiplied by 2. And I'll tell you where I'm at right now. I can't do all this all at once. It's too complicated for me. I'm coming up with, in my calculator, 0.25 to the 4th minus ri to the 4th equals 1.2434 something times 10 to the minus 7. Now let me finish this off. I wonder if I did that right. Okay. That's probably right. Plus 0.025 to the 4th. And then what I have to do is take that to the 4th root. And here's what I'm getting. Running out of room here. I'm getting the inside radius is 0.0227 blah, blah, blah meters. Now you see the outside radius is 0.025. The inside radius is 0.022. But this particular tube, it's a tube. You know what they said? It's a tube. Yeah, tubular shaft. Determine the smallest thickness of the tube. Okay, well, the smallest thickness of the tube would be this here subtracted from 0.025, bunch of O's. So I'm going to do that now. I'm going to subtract that from 0.025, bunch of O's. And I'm getting a thickness of the shaft. We're talking about the thickness of the shaft. I just need to have some room to write here. I think the thickness of the shaft will be greater than or equal to 2.284 millimeters. Now let's see how we did. This was problem 541, and I'm going to go back here and see if we got, thanks to Coy, I bet we got it right. 541 says here, 541, 2.28 millimeters. Hey, that's what we got. The book says 2.28 millimeters. Do I need to go back over any part of that? Well, there's a torsion formula for you. Now, another thing that I love to do is put loading diagrams. Loading diagrams. Here we could put the loading diagram for this. Do you remember? First of all, is there any question on anything on that? I guess you guys are all happy with it. All right. Now, you know I love loading diagrams. And I might ask you to do a loading diagram. It wouldn't hurt you any. Do you remember this shaft? How long was it? It was 2 meters long. Now, do we know what this torsion is that's acting on it? Yeah, there it is. See it? It's 625, isn't it? You have 625 Newton meters acting on it, 625 Newton meters. Okay. We're going to do the torsion loading diagram. This is a very simple one. How do you do loading diagrams? You take a left-hand section. See, if you section this in here someplace, can you see that you'll have to have 625 Newton meters going to the left? Well, going to the left is negative, so you got 625. But guess what? It's 625 all the way to the end. It's a negative 625 Newton meters, and we're done. Ta-da, we're done. We have just drawn the loading diagram for that problem. Now, another thing that you might have forgotten is the angle of twist. Do you remember that? It goes TL over JG. Now, do we know the torque? Yeah, it's 625 Newton meters. Do we know the length? Yeah, it's 2 meters. We know that. Oh, here's where that G thing comes in. I erased it, but it's in the back of your book. You could look it up again.
It's 75 GPa.
Yeah, thank you. Here, let me write that down. Just a minute. They have a name for that. They call it the modulus of rigidity, I think. Some people call it the shear modulus. It's 75 gigapascal. The J, we just did. I don't know where it went. Was it this? I'm not at all sure. But this is it here. See it? That's the J right there. See it? Oh, gee. Did we ever get the R? Oh gosh, I forgot what we were doing there.
Yes, it was 0.0227 meters.
Okay, here, let's put it in here, shall we? It's 0.0027. Is that what you just said? Is
Yes.
that right? Okay.
Hold on. It's 0.0227.
Oh, 0.0. Yeah, there you go. 0.0227 meters. Yep, good going. All right, so we can get the J that you're looking at. It's right here. In fact, we could just write this. We don't need all that stuff there at all. Okay, now there's the J. Thanks to Coy, we got the right number there in the denominator. And so you can get that J. The G is, all right, I'm going to shut up now. And I'm going to give you, I don't know, minute and a half, 2 minutes. Find the angle of twist of this thing. It's going to twist. Go for it. Find the angle of twist for it. Go. Well, I did that and I got an angle of twist. I wonder if I did it right. Here's what I got. I haven't checked it, but I'm getting 0.0848, but that's in radians. If you converted that to degrees, and I could be wrong, I need to check that. If you converted it to degrees, it'd be times 180 and divide by pi. Gosh, that's pretty big. I'm getting 4.86 degrees. Did anybody get that?
I got 0.085, which is close, I guess.
That is dang close. 0.085 is that dang close to 0.0848. Maybe one of us rounded off. That was Heath, wasn't it?
Yes, sir.
Well, how about somebody else? Anybody else getting that? Or do I need to do it again?
That's what I'm getting.
Well, there's another person. How about another
Yeah, me too.
I bet that's right. I bet I did it right. Well, that's a pretty good twist for 4 degrees. Interesting. Well, okay, we had a little tiny bit of review there. You're aware that you could have questions about torsion on the test. Do you have any other comments or questions before we sign off here?
When will you be posting the final and when is it due?
It's going to be posted Sunday afternoon, as Sunday evening, whenever I can get my daughter to help me post it. I might be able to figure it out myself. I'm learning this stuff. Can't tell you the exact time, but it's due Wednesday night at midnight. It gives you 72 hours, doesn't it? Let's see, Sunday night, Monday night, Tuesday night. Yeah, you got it made. You'll be fine, except for those of you that have 4 of my classes. They don't have it made, do they? But you'll be all right. You can do it.
Just to double check, that's when the dynamics
Yeah,
test.
they're all going to be like that.
All right, thank you.
Thank you so much. Anybody else? Well, okay, it's been fun, but all good things come to an end, right? How do I get out of here? Let's see. Hopefully I'll see some of you again. I'm hoping for other classes.
This was my last.
Oh, that's
semester at
scary. Oh, you
TCC.
scared me. I'm sorry, somebody said something.
I was saying this is my last semester at TCC.
Oh,
so-
no, it's sad. Well, you come back and visit me when you're rich and famous, okay? I love
Well, I
it.
hope to be rich and famous, but I doubt it.
Well,
All right, thanks, Dr. Griffin. It's been a
oh,
pleasure.
it's been a pleasure. I've got students out there that have their own companies now. Okay, well, I'm going to say goodbye to y'all. A little Southern talk there. Y'all, goodbye for now. Okay, I'm gonna end the meeting.